So here again, this means that you set this to 0 if P divides the ideal. So you have to do something. So okay, and okay, so from now on, then we're going to talk about the case of weight F, weight 2. So you're going to recall a theorem of Hida. So if F is weight 2 and P is a prime that divides exactly n, and then sort of so this means that AP is plus minus 1. Then a theorem, yeah, this is a particular case, asserts that there is a unique p-adic family which sort of goes through F. So there is a unique p-adic family such that F2 is the given F. So somehow you can extend F2 to a p-adic family. So
everything is actually eigenforms. Everything is actually eigenforms.
Yeah.
The family.
Yeah.
So also here in this definition, what kind of values could K take?
Well, just K. I mean, I guess K in some condition. Well, in this case, so if you want to read this, it means there is a p-adic neighborhood of 2, such that the Fk is defined in this neighborhood.
Okay.
So I guess K has to be congruent to 2 more P at least, and maybe more. So now the key thing for what I'm gonna say next is that since A sub P is a p-adic unit, it's plus minus 1, then it has to still be a p-adic unit and for the whole or in a neighborhood of 2. Well, I guess the whole thing. So so AP of K is a p-adic unit. But for K bigger than 2, it means that Fk is actually old at P. So therefore, Fk is old at P for K bigger than 2. Say integer bigger than 2. And this is a key fact. So this means we can actually consider the corresponding new form, which has a lower level. So we can consider F, they call it F sharp of K to be the new form corresponding to Fk. So this just means the eigenvalues are the same outside P. So, and Fk sharp is modular form of weight K and level M, where I'm writing N equals P times M. Okay.
So sitting in here, how do you construct Fk sharp? How do you construct FK sharp?
So since f is all, fk is all at p, it must come from a modular form of level n, divided by p.
Why does it have to be a new form?
Hmm?
Why does the form of level m have to be new? Why couldn't it have lower level?
It comes from a node.
Well, if f was new here.
Oh, okay.
Yeah. Okay. Yeah. If f, I guess if f is new here, then f sharp k has to be new here. So so now now we can apply Shimura correspondence and Conant's formula to this, and
You're reading the degeneracy of which one it is.
so
If it's under the
f sharp k is going to correspond to some modular form gk in plus 1 or 2 of level m.
Wait,
Well,
so
level
wait,
4
what's the
m.
difference between fk sharp and fk? Do they have exactly the same Q expansion? Or it's almost the same except that for
Except-
coefficients dividing p?
Yeah.
Okay. So
So
fk is not a new form. It's just some form. And fk sharp is an actual honest to goodness new form of the lower level.
Oh, this
So
is
And
this
there's
is
the
what
unique
is-
one.
The LCs of this is not primitive, so you're just changing the factor of p to make it primitive.
Yeah.
So this is what is it called, like P stabilization or something? You see that?
It's the ordinary
Yeah.
destabilization of
Yeah.
FK sharp.
Yeah.
So, okay, and now if this form is some ck of d due to the d, then now we have formula for special central values of twists of these forms, except the formula works for twice as many discriminants, and that's the key here. We're going to have a formula because m has one less prime dividing. We have twice as many discriminants that for which Conant's formula works. So I'm going to call this type 1 discriminants are going to be discriminants, well, the discriminants minus d, such that, say, minus dl equals wl for all l dividing n. So these are the discriminants for which Conant formula applied to start with. I mean, the formula in way 2 applies. And so, and here we can say something about the special, Conant's formula say something about the special value of the value. But then we have the type 2 discriminants, which are the ones that have this true for all L dividing M, but they have minus, at P they have the opposite sign. And so in this case, since, I mean, in this case, the sign of the functional equation is positive, and in this case the sign is negative. So one would be interested in derivatives. So this is what, let's say, Conant's formula gives us this, and then we would like to get this in this case. So. So, okay, now, in order to relate things that happen at weight 2 with these coefficients, we need to have some sort of control about how these coefficients change when k changes, and there is a theorem Hida and Stevens that says that if you pseudo normalize the coefficients of these forms, have to do some normalization, then so normalize the coefficients, these coefficients to, I'm going to call C triple the normalized coefficients, then they extend to periodic analytic functions. Okay, and still then Conant's formula, well, it's just what it says. So Conant formula for D of type 1 says that C K of D is some constant times, sorry, C2, the specialization of T2 is some constant times square root of D times the central value, minus D. And for type 2, Conant's formula says that this is actually 0 for discriminants of type 2. Because, well, but we know that the sign of functional equation is -1, so it better be 0. Okay, so now what can we say about then about the derivatives? And so this is our main result. So this is 3 simple derivatives. So so this is sort of the I'm going to call this theorem A. So if minus D is a discriminant of type 2, then there exists a point. Sorry. I'm going to make an assumption that F, so F is weight 2, and I'm going to just assume that it has a rational coefficient, so it corresponds to an elliptic curve, or Q. Just to make the statements easier. So, and so our theorem says that, that there exists a point in the twist of E by quadratic character of conductor D, rational, such that the derivative with respect to weight of this coefficient. Okay, so this coefficient vanishes at 2, so I could take the derivative at k equals 2 is actually the periodic logarithm in E of this point. So here, just think of this point as being a point defined over QP, and take this parameterization and take the periodic logarithm.
But it's actually rational. It's actually
it's actually rational. But, yeah.
So who proved this theorem? Who proved this theorem?
This is the theorem.
This is the theorem.
Yeah. Yeah, this is sort of the main theorem. And so this is 1 and 2. In fact, P sub D is non-torsion if and only if L prime minus D at 1 of course, the way to actually prove this is to use Heegner points, classical Heegner points.
So,
And,
so this condition below, isn't it always guaranteed by the work of Waltz Piaget?
what condition?
The condition on the L series, on the non-vanishing of the derivative of the L series. He
Yeah.
had the result that, according to the sign of the functional equation, guarantees a twist where either the L function or the derivative of the L function doesn't vanish of this twist in the central value.
This is a statement about.
I'm talking about for any D of type 2, I'm saying that the point that construct sort of vanishes if the.
No, but what I'm saying is that you should shouldn't you always be able to find such a D for which
Yeah.
with this
So-
property?
That's
We
not
always
Gonzalo
have a-
Tornario. I think Gonzalo Tornario only goes for special values. I think it's
Maybe that's dumb.
yeah. Yeah. So the point here is that this derivative somehow is related to the special the central derivative. That's sort of the point. So if one is able to sort of in a sense this you package all your information in a p-adic family rather than a classical modular form, and so let's write G tilde for the normalized modular form of half integer weight or p-adic modular form or whatever that is, and so if you sort of what this is saying, it sort of you write this as a power series in k minus 2, say. So the constant term, this is what you get when you evaluate at 2, is just the modular form of weight because. So you get you get this for D of type 1. This is just the specialization to weight 2, but then you get another term, k minus 2. So when you take the derivative with respect to k, you get the following. You get the sum over D of type 2 of the logarithm p sub t reach d, and then of course, well, you get something similar terms. So in a sense, what I'm saying is that the sort of p-adic Schiller lift of f is sort of packaging the information about the special values, but also about somehow about the derivatives. Okay. So you can actually use Grossanger to come up with the explicit formula for these.
What does normalize mean? Just set the coefficient of Q to 1? What is the tilde over the GK? And like the tilde is over the CKs. What is the normalization?
For this, it's something like so basically you find a discriminant for which the coefficient is not 0 in a neighborhood of 2. That you do by Waltz-Boucher.
Okay, so it's really a choice, and then PD is dependent upon how you normalize things.
Yeah,
This
yeah,
may
yeah,
not be
yeah.
generated because you might pick the wrong normalization.
Yes, that's true. Yeah. So yeah, there should be a
Yeah, okay.
another
Yeah, it's just trying to understand.
yeah. So yeah, this the way you construct these are or you prove this this part. These are Stark-Heegner points, and so you need and then you're taking sort of trace with a genus character, and the product of the two discriminants has to be positive because Stark-Heegner points are defined over real product for this. And then to prove that the point is actually a global point, so in principle, the Stark-Heegner construction gives you something over QP, but if you want to prove that it's global, you have to go to, you have to use gross idea. So that's.
So can you say again how you deduce it from gross idea? The point is global.
Well, essentially, you find that's actually previous work of Bertolini and Darmon. So you actually, what you do is you actually prove a formula, sort of a gross idea p-adic formulas relating this with this, and then you just show that, well, you can construct a Heegner point whose height is the same, so whose logarithm is the same, so the point has to come from the global.
It somehow relies on previous work of Gross, right? on also Heegner points.
Maybe. I'm not sure. Yeah, maybe. As I understand it, you compute a formula for the logarithm of the point, and then you prove that there is a Heegner point with that logarithm, so it has to come. And that you do because you have the Bertolini-Darmon formula relating this for the Stark-Heegner point, and then you have gross idea formula relating this for the Heegner point. Okay. So so there are some remarks here. So notice that when the analytic rank of E sub D is of E minus D, analytic rank is less than or equal to 1. So either the central value or the central derivative does not vanish. Then what this is saying is that the analytic rank is actually the order of vanishing of the coefficient at weight 2. So one could ask, what is the order of vanishing at k equals 2 of this coefficient in general? So if the analytic rank of the curve is less than or equal to 1, then this proves that this is actually equal to the rank. So, and also, in the case of the analytic rank is 2 or more, then this vanishes, and so you can ask what is the leading term. So okay. So well, one can ask whether you can actually use this to compute, to do the same, to compute, to find all these, a large family of these, for a large family of these, which must have a central derivative vanishing. So that's something you can do with Connell's formula, or Wells-Boucher formula in general. You can actually compute a modular form of weight 3/2 and look at the coefficients, and if they vanish, then the LCS vanishes. So you can have some experiments about how many vanishings you have. So you could ask whether this is useful to actually find to find the central derivatives that vanish. And of course, since this is sort of p-adic, you could use this to prove that you can compute this g sub k to some p-adic precision, and then use it to prove that some central derivatives do not vanish. But then you might wonder whether the ones that give you 0 up to your precision, maybe the derivative doesn't vanish because you need more precisions. So and then how to compute this, I don't know, but it might be possible to do some sort of periodic version of gross points and gross formula and end up with some sort of periodic beta series or something that with which you can compute this, but always to some periodic approximation. So I like 5 minutes.
I think you're a little longer than
Yeah.
So how do we prove this? Just to give an idea. So the main ingredients are first another formula of Conan. Not for the, which is gives more information about the coefficients of modular forms of half-integral wave, and actually relates the product of two coefficients. Say for two, let's say K here. So for two discriminants with something I'm gonna call gamma K1, 2, K, which is some integral of some algebraic cycle, some geodesic cycle, as in Gintani's construction of so that's the first ingredient. So the second ingredient is a theory of Stark-Heegner points. Stark-Heegner points, which actually relate the derivatives at k equal 2 of these integrals with Stark-Heegner points. Let's say this is related to the Stark-Heegner point P sub D1, D2, which essentially is taking a Stark-Heegner point, which is defined similar to a Heegner point, but it's defined over Hilbert class field or ring class fields of real quadratic fields. So D1 times D2 is a real quadratic discriminant, and then taking a trace of that with a genus character corresponding to this composition. And so, but in principle, in general, Stark-Heegner points are sort of periodic points with the curve, which conjecturally, so they only are they are defined. I say they are defined over ring class fields of real quadratic fields, but that's only conjecturally. In general, we don't know that, but. So in order to get that statement about there's a global point in something else, and that's a theorem of Bertolini and Darmon, which actually claims that under certain assumptions that hold in this case, P D1, D2 is global under some hypothesis. So actually, I think the main hypothesis is that this. So the way you set up things, this this integral. You extend analytically with k, and then it's going to vanish for k equals 2, so you take the derivative. But sometimes, depending of this condition, sometimes this vanishes identically, so you actually don't get hold of the Stark-Heegner point in this way. So but with so the hypothesis might be something like this is not identically 0 with k, but in this case it works. So and so I actually want to say something about the Gauss concept. Okay, so that's the main idea of the proof. So let me see if I can say something quick about the Gauss concept. Which is so the Gauss-Consequent formula in a sense you can say that is telling you that if you take all the classical Heegner points, if you take classical Heegner points and trace them down in this way with some of the discriminants changing, and then you package all these points in a sort of a formal Q expansion, then you actually get something that works like modular form of weight 3/2. So in other words, all these Heegner points are in a line, and the ratios are coefficients of modular forms of weight 3/2. So Gauss-Aguirre formula tells you that that's true up to sign, but then Gauss-Aguirre says that that's true and even with the sign. So to speak, the Heegner points, the height of the Heegner points is the central value, and the square of the coefficient of the modular form of weight 3/2 is also the central value. But so that means that the Heegner point is essentially a multiple of a generator with the constant is just the coefficient, but there's the question of the sign. So you're actually saying that the Heegner points go in the direction of the sign of the coefficient of the modular form, something like that. So and so the Gauss-Aguirre type formulas that we would like to prove are similar formulas for Stark-Heegner points, and we are able to prove. I'm gonna write it down. We're able to prove that for some under some assumptions, which in particular you need the level to be divisible by at least 2 primes, so that the proof works. But it actually, so that's what I wanted to show here. Actually, the case of prime level is actually the easiest to compute, and that's what we actually started doing. And let's turn on. Working. No. So on the left there's magma with which there's this program by Darmon and Robert Pollack that actually computes the Stark-Heegner points. It sort of takes a long time. So here's a computation I have running somewhere that is trying to compute this. Well, I didn't say what it was, but it's these traces of Stark-Heegner points for the elliptic curve of conductor 43. And so it's been computing for a couple of hours.
So what does this mean?
So this means that for discriminant, well, you take discriminants, you trace what is it? You compute the, so in this case it's just plain old traces. So you compute the Stark-Heegner point for quadratic field of real quadratic field of discriminant 89, and then you trace it down. You check that it's actually a global point. You don't know how to prove that, but you check that it is a global point, and then this is what's the multiple of the generator that the point that you get is. So if you do this for 89, you get the same as for 33, and then for this discriminant you get the triple, and so on. So it's just saying in which direction the points go, and on the right, I have my programs to compute modular forms of half integral weight, which are in Paris. And so if I run this, I actually, so it's done. It's already finished for discriminant up to 5,000. If we find, so this should be the same. So this is computing coefficients of modular forms of weight 3/2. Which is this is not the modular form of weight 3/2 that I talked about before, because this one gives central values for real quadratic twist. So it's a different Shimura lift. But you should see that the coefficients are the same as here, in the sense that they are. We expect the coefficients to be the same up to sign, if you assume that the point is global, whatever. But they actually match. The signs match. So well, anyway. So it's just curious that the easy case to compute is the one that we don't know how to prove. So we can prove the case of several primes, and yeah, and we can still get experimental results that are not about something that is proved. So it's still.
So here on the left, you mean the easiest case. So this is the easiest case to compute the left side. Or
No. This is it's computing. It's slow. And you saw how I started this at I don't know. I think at like 8 a.m. It's only computing. So it's computing. It's sorting the discriminants by residue classes mod 43. So it did the whole thing for 2 mod 43, and now it's doing the thing for 3 mod 43. And this took like 5 seconds or something. So this is computing the Stark-Heegner points. It's kind of hard, because you have to compute the point. It's the same as with classical Heegner points. You have to compute it to enough precision, p-adic precision, and then figure out that it's a global point, find the global point.
Are you on the left side? Are you recomputing the? Is this called? I mean, when you compute the Stark-Heegner point, you first compute these moments of p-adic L functions, then you take some.
No. Yeah, the moments are pre-computed. It takes like a day to compute it, to pre-compute.
Oh, but you're okay.
Yeah.
And on the right-hand side, are you? Can you
But I'm using a precision that is probably too high, because I set a precision so that the computation runs for up to discriminant 5,000, but probably for discriminant 89, you can use lower precision. So I'm not being very smart about this side. I'm just checking that the signs match. I mean,
and this can you actually get the points here from just looking?
No. You get the gross points, something like gross points. So this side, what you're doing is computing the modular form of weight 3/2 as a linear combination of some sort of generalized theta series. So, by the way, this is actually work with Mao and Fernando Rodriguez that give us formulas for computing these modular forms as the generalized theta series. Yeah, so it's really fast. So this way, one can compute I don't know, millions of coefficients. So Mike Rubinstein has taken this something like this and computed like 10 to the 8 coefficients or something like that.
On the left-hand side, the numbers in the second column are the indices of the Stark-Heegner points. And the,
Yes.
And on the right, you compute those
I
quantities.
compute the coefficient.
Okay, so that's like a ratio of the sizes of each other.
Well, that's what is it? Yeah. Yeah, the ratio of two of these guys when they are not zero. Yeah.
The square of that ratio of
The square of this, yeah, the square of the quotient of two of these is should be, yeah, is equal to the ratio of the Th of each groups. And yeah, and then you're getting a particular square root. Yeah, but no, I'm not computing it that way. It's just counting points and ternary lattices.
And the zeros should be when the rank is bigger than 1?
The zero should mean that the rank is at least 2. Well, yeah, the analytic rank. So yeah, which should mean here that the point, the Stark-Heegner point is torsion. I don't know if this curve has torsion. So. Okay. Questions?
So we seem to already start the questions during the talk, but I mean, does anybody have any more questions for Gonzalo? No, let's take him dead. And then we'll have 15 minutes, so the next talk will start at 10:40.